Now, the third lecture by Michel Goemans.
Thank you. Thanks for coming back so early in the morning. So let me first start by looking at some of the concepts we saw yesterday. I'll be talking a lot about stable sets and perfect graphs today. So yesterday we defined the following concepts. Given a graph, alpha of G is the size of the largest stable set. So that's a set of vertices in the graph such that there are no edges in between them. And you can also look at the size of the largest clique. So that's it's a complete subgraph, complete induced subgraph, and omega of G is the size of this largest clique. And so the first obvious relation is that the size of the largest clique is at most the chromatic number, chi of G. So chi of G is the minimum number of columns needed to column all the vertices of the graph properly, which means that it's the smallest number of stable sets that cover all the vertices. And this is simply because if you look at the largest clique, then every stable set, so every column class in a coloring can use at most one vertex of the stable set. Now, when you so similarly, you have that if you look at the size of the largest stable set, you can complement everything. So this is the same thing as omega in the complement. And so this is also at most the chromatic number of the complement. The chromatic number of the complement, I'll just write it as chi bar of G. So that's the smallest number of cliques covering all vertices. Now, yesterday we introduced the notion of a perfect graph, and so let's look at two classes of graphs. One is that for any induced G prime, we have equality. So alpha of G prime, omega of G prime is equal to chi of G bar. And another class of graph is for all induced G prime, we have that alpha of G prime is equal to chi bar of G prime. So this is always. And so yesterday I defined this class as the class of perfect graphs. In fact, implicitly I was using the fact that these two classes are actually the same, and that's a result of Vars. In fact, what Vars showed was that this is equivalent so this is Vars 72. He showed that this condition is equivalent to saying that for all induced subgraph, you have that omega of G prime times alpha of G prime is at least the number of vertices of the graph. And so that's clearly symmetric when you take the complement. And so that means that Vars also showed that this class of graph is equivalent to that class of graph. Now let me, and yesterday we defined the stable set polytope as stab of G, and we said it's just the convex hull of all incidence vectors of stable sets. And then in particular, I can, so if this is stab of G, the following inequalities must be satisfied by every stable set, and that's simply saying that if I take any clique, a clique and a stable set intersecting at most one vertex, and so the sum of these xi is at most 1. So now if I take all cliques and consider all these inequalities, I get a polyhedron Q stab of G defined in that way in terms of its facets, and that contains stab of G. And so yesterday I introduced an SDP, the theta body, that is that for any graph is sandwiched between stab and Q stab. And in addition, I mentioned that for perfect graphs, you have equality between throughout. So stab of G is equal to Q stab of G, and also, so that means that you have equality there. Now, I'd like to correct something I said yesterday, which was incorrect. So someone asked a question about the strong perfect graph result and whether that led to an algorithm for computing alpha or omega, and so this is not the case. So the decomposition algorithm has been refined, but it has been refined to show that you can recognize in polynomial time if a graph is perfect. However, it's not known how to optimize these quantities over perfect graphs using just the decomposition theorem. However, you can optimize, you can compute these quantities in polynomial time using SDP, because SDP can be solved efficiently up to an arbitrary precision in polynomial time. Now, let me first give you some examples, just in case you haven't been playing with graphs, you live purely in the continuous world. So let me show you a few basic classes of perfect graphs, and let me show you a few things. So first, let's take the case in which G is a bipartite graph. So what is the largest clique in G? Well, it's pretty obvious. You can take at most 2 vertices in a clique because it's bipartite. So this is 2. What is the number of columns you need? You need only 2 columns. And so the chromatic number of G is also equal to 2. And if you take an induced subgraph of a bipartite graph, you still have equality. So that means that a bipartite graph satisfies this. It's perfect for that notion. Now, let's look at what this means. So what is, if you have a bipartite graph, what is alpha of G? Well, it's the size of the largest stable set. It's not true that it may be one of the column classes. It might be that if you take this vertex and, so vertices from both sides, you might get a larger stable set. But so that's the size of the largest stable set. And what does the clique covering number mean? So what is chi bar of G? Well, that's the smallest number of cliques that you need to cover all the Vancies. So you could try to take a matching and then add some not everything is covered. In this case, everything is covered. But so this is known as the edge covering number. Edge covering number of the bipartite graph. So, so if I was using low Vars equivalence, then this would show that since this is trivial that you have equality, so that's trivial. So this would imply that the edge covering number of a bipartite graph is always equal to its stability number, and this is known as Koenig's theorem for any bipartite graph. The stability number is equal to the edge covering number. So that's a typical, it's a typical min-max relation. This is the minimum number of edges required to cover all the Vancies. That's a maximization problem. That's maximizing the size of the largest stable set. So that gives you a good way of checking if, let's say, a stable set is maximum, because as a certificate, I can show you an edge cover whose size is equal to the size of the stable set. So that's an NP intersect co-NP characterization of these quantities. It doesn't give you an algorithm, though, to compute alpha or to find the edge covering number. Although these can be done easily. Let me give you another example. If I take a G is a comparability graph, so in that case, so that means that the edges can be oriented into a transitive acyclic digraph. So you want to orient the edges in such a way that it's transitive. Every time you have a directed path, you have also the edge, the shortcut edge. And so if you take a comparability graph, what is for example, the largest clique? The largest clique in the graph, if you think about it, it's exactly the same as the longest directed path in that digraph. So it's the number of Vancies in the longest directed path in H. And what is the chromatic number? The chromatic number, you have to use for the chromatic number, you have to use stable sets. So what is a stable set in that case? That's a set of Vancies that cannot be compared in that digraph. So that's the this is typically called a chain, and so the chromatic number would be the minimum number of Vancies in what's known as an anti-chain. And so what we have indeed that comparability graphs satisfies this at equality because of Dilworth's theorem. So Dilworth's theorem says that you have equality, so that for any for any digraph, the largest chain is equal to the no, what did I write? Minimum number of anti-chains covering minimum number of anti-chains covering. So Dilron theorem is that omega of G is equal to chi of G. So I mean, I could give you lots of other examples of graphs for which that are perfect, for which we have equality. But what I'd like to do instead is I'd like to instead of continuing giving you examples, I'd like to prove this equivalence, and at the same time also proving this. Might be a bit ambitious to do a full proof on the in the lecture, but I'll try. So so let me and the proof is going to be polyhedral. So this is, you might say, I mean, let's say the equivalence of this and that. It may not look polyhedral, but you really need a polyhedral approach. You really need, in particular, you'll see we'll be using duality in proving this. You really need that in doing so. So let me first look at a weighted version of the largest clique. So let me define so suppose I have weights on the vertices of the graph, and now suppose I'd like to look at the maximum weight clique. So one way I could define it is the following. I could say I maximize the sum of wi xi. I'd like xi to be the incidence vector of a clique, so I'd like this to be 0, 1 for every I. And then I'd like it to be a clique so that I will impose that for every stable set, I have at most one vertex in the stable set. So this is an integer program defining the maximum weight clique in a graph. And then I could relax these and get a linear program. So I get an upper bound, which is maximizing sum over I, wi xi, subject to x satisfying all these constraints, and also xi being non-negative. So what I can, so let me first write it down. But this is really the same as Q stab, except it's for the complement graph. So this is Q stab of the complement. And now I can use LP duality. So what does LP duality tells me? Tells me that max is equal to a min. In the min, I have a variable for every stable set, and so I'd like to minimize the sum over my stable sets S of ys, and then I get that for every I in V, I have that if I look at all the stable sets containing I, this should be at least wi, and ys is non-negative. And so what does that mean? Suppose that I could find an integer solution to this. So this is a linear program, this is fractional, but suppose I could find an integer solution to this. So then it would mean that every stable set is as an integer multiplicity, and then what my stable sets do is that they cover each vertex wi times. So if the w's were 1, it would mean that this would be the chromatic number once I put the integrality. So this, since I'm further restricting, this is at most when I put integrality constraint, I get the chromatic number of G, but with for a weighted chromatic number of G. So every vertex has to be covered wi times. So so imposing that, for example, the largest clique is equal to this means that throughout here I have equality when W. So if I'd like W takes values which are either 0 or 1. 0 allows me to go to induce subgraphs. 1, if all the wi's are 1, I'm really defining W of G, omega of G, so the clique number and the chromatic number. So the first step of, so there are different ways of proving, for example, the equivalence between this and that. But one key idea is to use a replication lemma of Vars, and so what it shows is the following, that if G, so again let me say that this is what I will call G is perfect. So replication lemma of Vars is the following, if G is perfect, if I take a vertex V and I look at its neighbors, and then I duplicate it, meaning that I put a new copy of V, I put an edge between them, and I link that new copy to all the neighbors of V, same neighbors. So N of V, the neighbors of V is equal to the neighbors of V prime. Not quite, because the neighbors of V contain now V prime, and the neighbors of V prime contains V, but kind of. And so when you do this replication, what Vars showed is that this new graph, G prime, is also perfect. It's not too difficult to show. We could show it, but let's skip it for now. So once you have this, it's actually not, I mean, it's pretty straightforward to get that perfect means that here you have equality throughout. So this would mean, because you can essentially replicate a vertex not just once, but you can replicate it, let's say, wi minus 1 times. And so, because you can always assume, by scaling, you can always assume that, I mean, first you can assume that this is a rational, and then by scaling, you can assume that this is an integer. So, so that shows that if you have this condition, then in fact, you would have equality throughout. So this would be an equality, and this would be an equality. Now, in particular, this being an equality means that since this is true for every W, it means that the convex hull of stable sets is given by these inequalities. So that's Q stab of G bar. So it means this implies that the convex hull of so Q stab of G bar is equal to Q stab of G bar. Okay, so that's a good step. But it says more than that, in fact. So this is a very important notion in discrete optimization. So not only we got an integer solution in the primal, but we have also an integer solution in the dual. And so that's so it's a stronger notion. So it's related to the notion of total dual integrality. And in fact, having a solution, an integral solution in a dual for every W that's integer, actually implies an integer solution in the primal. So if we had been able to show just this equality for every Wi that's integer, then that would have implied that equality as well. It's an interesting notion of TDI-ness, which I will not cover. But so now what I want to do is I want to derive that from the integrality in this dual. I'd like to derive that that I have also the same property for Q stab of G. So what I'd like to, so this plus this integrality of the dual, I want to show that this implies that stab of G is equal to Q stab of G. So let's do this.
Question?
Yeah.
So this holds for only positive integer vectors or non-negative integer.
Yeah, I swept that under the rug. So the thing is that if some Wi is negative, you'd better not include it in the max clique, because that would only decrease the value. So you can actually eliminate these, but once you show it for non-negative ones, you can then show it also, because you're essentially taking an induced subgraph. So it's true for every W.
Michel, just before we go on, so again, how do you apply the replication lemma to get equality? What's the...
So the replication lemma would be the following. So the replication lemma, I would say that I would take so I have a graph and I have a W. Like for example, I have, let's say, this graph and W is 2, 3, 4, and 1, or 0. Let's say 0. So what I'm going to do, or let's say 1 for now. So what I'm going to do is I'm going to duplicate these once, duplicate these twice, these 3 times, and then I'm going to put a clique here, a clique here, a clique here, and so on, and then join them, do all the connections, and so I get another graph, but from this replication lemma, which I haven't proved, so I would need a proof of it, but it's not that complicated. Then from that, I get that this new graph is perfect. Now, in this new graph, you can show that the largest clique in this new graph correspond to as the same value as the largest weighted clique in the original graph. That's one thing. And then you can also reinterpret these coloring number in the original graph and in the in these duplicated graph. And so because the graph is perfect, for this graph with unit weights, you know that this is equal to that. And so you have equality throughout. Okay, so it's very simple, nothing fancy. So now let's look at Q stab of G. So we take, we'd like to show that Q stab of G is equal to stab of G. So let me take a vertex of Q stab of G, or actually maybe not necessarily a vertex. Let me take any point in Q stab of G, and I'd like to show that it's also in stab of G. So what does it mean for a vertex, for a point to be in Q stab of G? So, so we haven't proved that yet, but so let's say let x in Q stab of G. So being in Q stab of G, it means that for every clique, I have a weight of at most 1. So let me first assume that x is rational. So if x is rational, I can find an integer q, let's say, such that xq is an integer vector in V. So what it means is that if I look at, since I know that for every clique, sum of xi is at most 1, it means that sum of qxi over every clique is at most q. So it means that if these are the weights, if these are my weights, it means that the maximum weighted clique in the graph is at most q. So that means that omega in G with respect to these weights qx is at most q. But I just derived this. So it means that I just derived that omega of G for a vector W is equal to chi. So this is equal to chi of G qx. And so this is at most q. So what does that mean? It means that the weighted chromatic number of G for these weights is at most q. So it means that I have a bunch of stable sets. I have at most q stable sets. Let's call them S1 up to SQ, let's say, such that if I look at the number of stable sets, that cover I have at least Wi of them, which means that at least qxi covering I. Now, I can, if I have more than that covering I can remove some vertices from some of the stable set to have equality. So I could say with qxi stable sets covering I. But if I have qxi stable sets covering I, when I divide by q, it means that I have a convex combination of stable sets giving me x. Because I just have that the sum of the 1 over Si over I is actually equal to, this is equal to qx. So if I divide by q, I get a convex combination, because I have q stable sets, I have a convex combination giving me x, which means that x is in stab of G. I'm starting to regret to do a proof on the board, but it's okay. So what did we show? We first showed that if we assume this, then using this replication lemma, we can first get that stab of the complement of G is equal to Q stab of the complement of G. But we could also show a stronger result that we had an integer dual solution. And from that integer dual solution, we actually derived that Q stab of G was equal to stab of G. So it means that in that case, we have this sandwich. On theta body is indeed equal to stab of G, and on theta body is indeed equal to Q stab of G. Now, let me at least finish it. I'd like to go here now. So I'd like to show that this is true. But so now that's very simple, because what is alpha of, let me first say that I take the entire graph. What is alpha of G? Well, alpha of G is obtained by maximizing the vector of all ones over the stable set polytope. So alpha of G is, I take alpha of G, I maximize in the vector of all ones, and I get some stable sets that are maximum. Now, I know that stab of G is equal to Q stab of G. That's what I just proved. So if stab of G is equal to Q stab of G, it means that I have these, I can use LP duality because I have a complete description of stab of G. So I have a complete description of Q stab of G in terms of linear inequalities. So it means that by optimizing over stab of G, I get a corresponding dual solution. Now, dual solution will put weights on cliques. So we'll put weights on cliques. So now let me take just one clique in that dual solution that has a positive weight. So by complementary slackness, that will say that that clique intersects every maximum stable set. So what I have now is I have a so the fact that stab of G is equal to Q stab of G means that if I look at alpha of G, and I could have done it for any induced subgraph, but I'm just doing it for the graph, I have that there exists a clique such that the clique has a non-empty intersection for every maximum stable set S. But that's good because I take my clique, this is my clique, and I delete that clique. So I take the graph minus the clique. How will the stability number of that graph be? Well, it's going to be at most the stability number of G, but it cannot be equal to that because every maximum stable set intersects my clique. So if I delete my clique, I lose 1. I must lose 1 because if I delete the clique, since every stable set intersects my clique, every maximum stable set intersects my clique, I lose at least 1.
So it's less than or equal to?
It's less than or equal to, but it's also equal because a stable set can have at most one vertex in common with a clique.
Oh, yeah, sure. Right.
So you have equality here, but by you can continue. You can go to this induced subgraph, and in that induced subgraph, instead of having all vectors 1, you put some of the wi's to be 0. So you can continue and get another clique, and again decrease the stability number by 1. And so what you get is that I will get a number of cliques. I will get a number of cliques equal to the stability number of the original graph. So that shows alpha of G is equal to chi bar of G. But I mean, implicitly, and I kind of mentioned it, you can go to the induced subgraph by just setting some of the weights to 0. Okay, so now we prove that this implies that, and vice versa, by doing this polyhedral proof in which we did show as a byproduct that the stability number of G is equal to the Q stab of G. So one thing I'd like to emphasize is that it was quite important not just to get integrality, but also an integral dual solution, and this was a key in getting the argument wrong. And you cannot always do that. If I have time, I'll show you some other examples in which this integrality in the dual is not true. So one question that I find interesting is that so you can decide if a perfect graph if a graph is perfect in polynomial time using these using refinements of the decomposition theorem that came from the strong perfect graph conjecture. But it would be very nice to be able to decide in polynomial time if a graph is perfect based on these theta body. So you know that stab of G is equal to the theta body if and only if the graph is perfect. And so would be nice to have a polynomial time recognition algorithm for perfect graphs based on these facts. So you could try, of course, to optimize in a direction, and then if you get a point that's not in, if you get a point of th that's not in stab, then you know that it's not perfect. The problem is that, of course, it could be like this, and you don't know how many directions you would have to take. So that's pretty obvious. Yes?
Even if we don't ask the recognition question, if we just ask certification, I'm trying to convince you that my graph is perfect. Is there like an easier, or is there any way that doesn't rely on the structure theorem?
No. So no, this is not fully understood yet.
Michel?
Yeah.
Is there any hope that, like, I mean, if you found a vertex that like wasn't integral or something like this, that you could transform it into like an odd hole or a non-cycle? No.
So but the certificate is compact, right?
The problem is that, of course, I mean, I can take a graph that's perfect, and I can add a little odd hole here, just in a little corner, and it's not going to be perfect. The problem is that you can look in many directions. It may not involve these odd holes. So,
the question is somewhat different. It's just if you to prove the strong perfect graph theorem, you need to prove that these odd holes and holes characterize them. And I was sort of wondering if you could have any hope of re-extracting a different proof, but from the fact that you have some non-integral vertex and like trying to use that to find.
But I mean, when you, yeah, possibly. I don't know. So, I mean, let me mention a quick related characterization of perfect graphs, which is nonlinear in which has a strong continuous, another continuous field to it, and that's through the notion of graph entropy. So suppose I have a graph G, and I take a probability distribution on V, and now let me define the graph entropy. So HGP with respect to this probability distribution to be equal to the following convex optimization problem. So it's minimizing minus the sum over I in V of pi times log of xi. So this is a convex function of x, subject to x belongs to the stable set polytope of G. So let's quickly see one case. Suppose I take the complete graph Kn. So when I take the complete graph to Kn, what are the stable sets of the complete graph? These are just a single vertex. And so in that case, the stability, the stable set polytope is just a simplex. And so when you do this, when you minimize this over the simplex, you get that this is equal to minus the sum over I in V of pi log pi. That's going to be the optimum, pi for every vertex. And so this is just the Shannon entropy. So one thing that one can show is that for any two graphs f and g, the entropy of the union, and by union I mean just take the union of the edges. So these are two graphs on the same vertex set, let's say. So both are v something, and so they have the same vertex set. And so the entropy on the union, one can show that this is actually, for any two graphs, this is at most the entropy. You have less than the sum. And so now you might, so let's see what happens when I put a graph and its complement. So for a graph and its complement, so for a graph and its complement, I get that h of kn of p is at most h of g of p plus h of the complement of p. And so, as I said, this we know what it is. It's the Shannon entropy of p. And so you can ask, when do I have equality? And so let's say it's the 5 Hungarian theorem. So let me try to. I need some help from Hungarians in the audience. And let's say et al. So they show that G G is perfect if and only if you get that H of P is equal to H of GP plus this for every P. So again, you can compute this easily. This is just, we could, I mean, if the graph is, if the graph is perfect, you can replace it here th of g, and so you get a semi-definite program with a convex objective function. Problem is that for some p, again, you might be unlucky, and you might have equality even though the graph is not perfect. So that's another little result that would indicate that maybe semi-definite programming could be used to decide if a graph is perfect.
So and what's the operational meaning of this graph entropy? Does it have like a...
yeah, so it does. It does, but I don't want to get into that. We can do that offline maybe. So let me mention, for example, that let me say just one thing, that this graph entropy, for example, has been, in terms of discrete application, it has also been used, for example, for the by Kan and Kim to do sorting of partial orders, in which, so if you start from a partial order and you have to decide which comparison to do next, so that to get a total order, if you'd like to minimize the number of operations, of comparisons that you'd like to do, you can use graph entropy to do this. Now, so how much time do I have? I have 6 minutes or so. Let me move to a different topic in briefly. So what we did was we obtained some min-max relations, and one thing that was important in the proof, as I said, was the integrality in the dual. Let me mention some other min-max. I mean, there are countless of min-max relations, but let me mention one that I very much like, and that has some nice, again, nice application that that no one knows how to derive otherwise. So let me. It's going to be difficult to do in 5 minutes. Let me say it this way. So suppose, so one problem that has been very much looked at recently is in terms of how well we can approximate it, is the traveling salesman problem. And the traveling salesman problem, we're given a metric space, and we'd like to find a term of minimum total length. And you can try to relax it. And so one way you could try to relax it, you could, in polynomial time, you can compute the so-called Ellen Kamp bound from 1971, which what you would do, for example, is to minimize over all edges of the complete graph underlying this CE, C is the length, subject that for every, if I look at every cut, I need to have at least 2 edges. in my term that, and so I'm going to write that as sum over E in delta S is that of XE is at least 2 for every S. XE not negative. Typically there are some additional degree constraints, but one can show you can remove them, so let's not bother with them. And so clearly, if I look at the value of the TSP or the value of this LP, clearly this is at least that. Now, suppose you can still get something in between, so you could look at what happens is if I insist that XE is integral. If I insist that XE is integral, I get that this means that in every cut I have at least 2 edges, which means that I'm looking at the 2-edge connected subgraph problem. And I will get a value that's in between CHK and CTSP. So a major question is whether the supremum over all C of the ratio between this and that is equal to 4/3. It's known that it's at least 4/3, and it has been proved 40 years ago, or 35 years ago, that it's at most 3/2, but it's not known whether it's 4/3. But you could ask an easier question, and what's the ratio between these two in the Vars case? So you could look at what's the supremum over all C of the cost of the TSP divided by the cost of the 2-edge connected. And in that case, one can show it's 4/3. And this is attained because you could have a metric in which you have, let's say, 2 points that are far away and 3 paths. And so essentially, the best salesman would have to go once, twice, 3 times and go back to the origin, spending, let's say, fond D. So if it is D, then this would be fond D. But the best 2-edge connected subgraph is just to take the 3 paths. So that ratio, the claim is that it's at most 2/3, and so this is a result of Monma, Manson, and Polygon. And there is a very easy proof if you use this duality for discrete optimization. So what do you need to do? You take the optimum 2-edge connected subgraph, whatever it is, and then you'd like to transform it into a term. So what you do is you look at the vertices that have odd degrees, because these are the bad vertices. You look at the vertices that are odd degrees, you let them be T, and then what I'm going to do is I'm going to add a subgraph. I mean, let's say I'm adding a matching on these. So if I add a matching, then all the degrees become even, and so then I can do the shortcut and get an upper bound on this. So that would show that this is at most. So I mean, we know it's at least 4/3, but so this would show that it's at most 4/3. So now, what you need to show that it's at most 4/3? You need to show that the cost of the matching on these vertices is at most 1/3 of the cost of the 2-edge connected subgraph. And so this is not that easy to do, but you can do, there is a very nice Polygon proof that shows the following. You say that, let me do the following, let me take my graph, let me put 1/3 on every edge of the 2-edge connected graph. And then I will look at the T-join polytope. And what is the T-join? What is a T-join and what is a T-join polytope? A T-join is simply a generalization of matchings. It's a subgraph which has odd degree advances in T and even degree advances not in T. So for example, you could take this path and let's say that path. That would be a T-join. And so you could look at the convex hull of all T-joins, and one can show that if I look at the T-join polytope and I look at everything above it, so if I add RE plus, so if I look at everything above it, it's actually equal to the set of X, such that for every cut S intersect T is odd, for every cut in which this is odd, that this should be at least 1. And now we are done, because if I look by putting a thorn, the thing is that I cannot get an odd cut that has at most 2 edges in it. Because if I take an odd cut, since my graph is 2-edge connected, the number of edges in the cut has to be odd. But it's an odd number, but it's at least 2 because it's 2-edge connected. So it has to have at least 3 edges. And so it means that since I'm putting a thorn on it, a thorn satisfies all these inequalities. And so it means that a thorn is a convex combination of T-joins. And since it's a convex combination of T-joins, it means that one of them is at most a thorn times this, because my convex combination has this cost. Now I'm mentioning this because if you want to prove that this is the polytope, you could try to look at the dual and so on. But in this case, you could not get an integer solution to the dual. The dual would be only half integral. So if the costs are integers, then in the dual you would get a half integer solution. So it's I mean, it's not very difficult to prove, but one can show this, and so that's. So let me over time. So so today I decided to do something much more combinatorial, because you probably were a bit sick of, despite the beautiful lectures of Pablo, of all these semi-definite programming, and you'll have a lot of sum of squares in the lectures to come. So I decided to do something purely combinatorial and based on min-max relation in duality. Thank you.
Questions or comments?
Good. Well, because it's the last lecture, so for people who are in the program and want to kind of get more immersed in this kind of reasoning, maybe from the continuous side, do you have any pointers for where a good starting place would be? I got to skip that because I took your course.
I forgot if it is 2,500, but it's so the 3-volume book by Lex Scriven is the Bible. So.
And it's very compactly written, so it's more like 8,000 pages.
Yeah, exactly. When you expand the proof, it's a bit more. So.
Great, then let's thank Michel again.